Welcome to the last and the third lecture on module 3. First 3 series lectures. So we started in this 3 part lecture is the idea of 2 level Boolean logic synthesis. So what was our idea? The idea was that we have taken a specification from high level synthesis tools. We have generated the RTL, and from the RTL we represented them as Boolean functions, and then we wanted to represent them as in terms of minimal number of gates. So if you think in terms of Boolean functions, then it will be in the minimum the functions has to be represented in such a form so that their minimum number of terms and in minimum number of product terms, and in each of the product terms the number of literals should also be as minimum as possible, so that they can be represented in using minimum number of gates. Then what we have discussed, then we have found out that any Boolean function you can be represented in terms of prime implicants. So what are prime implicants? Prime implicants are the implicants of the product terms, okay, in which product term is not totally included in any other term. That means the prime implicants are all necessary to form a function. Then the next what we saw, then we have seen that some of the prime implicants are essential prime implicants because they contain a mean term or some term or that is actually they contain some mean term which is not available in any of the other prime implicants. So that will make the prime implicant an essential prime implicant, implying that to represent the Boolean function, that essential prime implicants are to be there. Then again next what we have to do, then we have to find out that we have to select a subset of the prime implicants such that they cover the function. So what do you mean by covering of a function? Covering of a function means there for all the mean terms in the function there is at least a prime implicant which contains it. So this is in the nutshell what we have seen in the last 2 lectures, and in the last lecture of this 3 lecture part, what we will today see that how you can find out a subset of primes so that it covers the entire function. Then we have also said that when you have mapped the problem that for that minimum 2 level Boolean logic synthesis, that is implementation using minimum number of gates. So once we have found out the prime implicants, and then we have found out the mean terms, and then we make a constraint matrix which we have seen in the last class, then it just remains to find out a unit covering problem or a subset finding kind of a problem where you have to find out the subset of prime implicants such that they all cover the mean terms in picture. So now it no longer remains a problem of VLSI or circuit design, it will become a problem of computer science where you have to find, which is actually called the unit covering problem, such that you have to find out the minimum number of prime implicants or prime implicants with minimum weights or whatever you say. Even you can forget about calling them prime implicants, you can say that finding minimum number of columns of the constraint matrix such that it covers all the rows, and that should be and there will be obviously multiple solutions to that, and you have to take the solution which is the minimum cost. So you can give each cost to each of the columns, like for example if the number of terms in the number of literals in a prime implicant are more, so that it will have a higher weightage and so on. Then what we say, we have found out that we represent the whole problem as a constraint matrix, then we have found that the matrix size may be very large, but it can be pre-processed to bring it to a reasonable size, then we can apply the unit covering problem or the prime subset selection problem. So how do you do that? You have to first find out which are the essential columns. So if there are some essential columns, that means they correspond to essential prime implicants, you have to take them, you have to include those rows, and by including the rows you can find out that some rows will be already being covering. So you have to eliminate those rows and the column has been taken into account. Next what you do? Next you find out by row dominance and column dominance. By applying row dominance and column dominance, what you will get? You will find out that some more rows are getting covered and some rows can be eliminated and some columns can be eliminated by using the concept of row dominance and column dominance. Finally, you will have a small matrix where no more pre-processing can be done to minimize it. There we will try to apply some algorithms to find out which is the minimal subset of those columns that has to be taken to cover the matrix. So that in today's class we will be basically learning an algorithm how to do that. We will learn a technique which is actually called the branch and bound, which we will see. That is the branch and bound to find a algorithm for selecting a cover. That is what is the agenda of this class, and how will you do this. So before we go there, go to what is branch and bound. So today's solution, that is the branch and bound. So before going to the exact algorithm, just we will try to give you what is the idea behind that. Like for example, so we can, as we have seen in the last lecture, so this unit covering problem, we can represent it using a equation like this. Okay, so that means P1, P3, P2, P3, P1, P2, all these things. So you can have all ones, P1 1 equal to 1 to all P1, sorry, Pi 4. That is all of them dot dot dot, all these columns can be 1. This can be one solution which will definitely cover it. There can also be a solution to that, but which is not a valid solution, is all of them can be zeros. If all are zeros, obviously this is not a solution. But you can think that what is all the possible values to all the columns, it can be all zeros to all ones. Obviously, all ones is a solution, all zeros is not a solution, but we have to find out a proper subset. So, say for example 1 0 1, that means select first, third and sixth and so forth, there can be a solution. So, in other words, this equation or the unit covering problem can be also represented in terms of a tree. That is, if you consider each node as each node in the first level, we can consider that each first node root node corresponds to the first column, second level nodes correspond to the second column and so forth. So, the leaf nodes will correspond to one of the solution. So, if you take the leftmost edge throughout, like from the, for example, if this is your root and then you come down to this and this one is your leaf node. So, this and we can think that if all the left edges, so this one corresponds to pi1, this will correspond to pi2, this will correspond to pi3 and say this is pin, last one. So, if you take the left edge, say that it implies that I have not taken P1, I have not taken P2 and so on. So, this one will represent all zeros cases. Okay, and if you take the last one, so that will also be Pin and this one will correspond to all the ones. That means you have taken all the edges. So, in other words, what I am saying that the solution problem, this solution space can be represented in terms of a tree. And then you have to find out that we have to take a path to a leaf, so that not all the leaf path will be valid because they will not cover it, but some of the valid solutions you have to take. There will be corresponding to the leaf nodes, and there will be in fact multiple solutions, and you have to take the one which is having the minimum number of weight. And how are weights assigned? You can assign weight in terms of you can say very simple weight can be the number of prime implicants involved. That is, all the prime implicants have equivalent weight, and if you count them, so the solution which is having the minimum number of ones, like all zeros means no prime implicant is selected, all ones means all the prime implicants are selected. So, you can think that the more number of prime implicants selected, you add 1 to the weights. Okay, so, 1 prime implicant means weight 1, 2 prime implicants means weight 2 and so forth. So, if you add up everything, it will give you the weight. So, the solutions which will have the minimum number of prime implicants will be your solution. Now, even if you can go for a more finer way of thinking, then for each of the prime implicants individually you can put a weight, like it can be the number of literals involved in a prime implicant. Like if x is a prime implicant, it has a weight 1 say, and if if a prime implicant is ABCD, it is having a having a weight of 4 kind of a thing. So, you can devise new different types of weights. Okay. So, that will some of the techniques we will see, but the basic core idea is that the whole problem can be represented in terms of a tree. Okay, and there are multiple optimum solutions, and our intention is just to find one of them. So, there can be even say you can find 3 or 4 solutions, that is 3 or 4 subset of the prime implicants be taken, and all corresponds to say 3 prime implicants, then you have 3 solutions of equal value. But then again you can dig into finding out what the number of literals in each of the prime implicants, that can give you again a finer value. Okay, and again if I can represent the whole stuff as a tree, binary tree, so you can easily understand that it is an order of complexity is exponential, because the number of paths, or you can say the number of leaf nodes are 2 to the power n if n is the number of prime implicants. So, obviously this problem again is not a simple problem in terms of complexities, and it requires an exponential order complexity to solve the problem. So, this branch and bound algorithm, so is actually if you take it in a full fledged manner, that is you explore all the parts of the tree, then it will be a exponential time solution will be there, but then we will try to first see that if we can minimize this. Of course, the worst case the problem solution space will be exponential, but let us try to see how we can minimize it so that the complexity reduces a bit. That is, again we will come back to heuristics. So, in essence this what you say in essence this branch and bound and making a tree itself is an exponential order problem. So, what we will try to do, we will try to not explore all the branches, we will put some heuristics, and for some of the branches we will stop at some level, and then we will see that okay, this branch we are not going to try because it is not, most probably it is not going to give you a very good solution. So, at this point some heuristics are coming into picture, that is they are trying to estimate what can be the solution if you explore this branch. So, if you can find out that this branch exploring has no meaning because it is not going to give you a good solution, then you do not explore the branch, you go to another branch and try to do that. So, at this point your heuristics are coming into picture. So, the heuristics will tell you that do not explore this branch, this is not going to give you a solution. So, that heuristics will actually will estimate the solution for a branch in a very quick way. So, if I go on exploring the branch, then I am going to get a very exact answer, but that is actually going to take a long time for me. So, what I will do is that for each of the nodes I can try to estimate what can be the possible solution, or what can be the weights of the possible solution if I explore that path, and that will be done in a very fast manner, and obviously there is a heuristic. So, the solution may not be attractive, exact, it will give you a value. So, based on that approximate value you can decide whether to explore that path or whether to drop that path and try on another path. So, our complexity will come down because we will not be exploring all the paths of the tree. So, that is the idea. So, the branch and bound problem is the solution space is enumerated in form of binary tree, that is why it is actually becoming a binary search tree, that is the problem is becoming an exponential. A node actually, as I told you, corresponds to a column, the left and the right edge corresponds to the node being or column being taken or the column being not being taken. That is very standard. If you are going by this way, is not taken. If I come out by this path, then that node or that corresponding column is being taken. Okay. So obviously it may also be noted that for some columns there may be a node in the, there may not be a node in the tree, because considering some column may result in elimination of some nodes due to dominance, inclusion or essentiality. Just like as I told you that always, I mean there may be some node path you have to take by force, like for example if I select a node, that is a column, if I do not select a column, then some of the nodes or some of the mean terms or some of the rows in terms, because mean terms are represented by rows, so they may become essential, because there will be only a one in that row. So I mean that all the examples we will see by example. So that will become an essential row, and that will imply, sorry, that will imply a column to be an essential column. That is, by eliminating some of these nodes or by taking some of the nodes, you may land up to a situation that some of the prime implicants may become an essential prime implicant, and that by force you have to take that node corresponding to a prime implicant. So in that case there will not be two solutions possible, you have to take any one of them. That is, some of the solutions will start becoming invalid. Just for an example, you said you take prime implicant number 1, that is you select node number 1, and by doing that you eliminate some of the other rows. How you eliminate? Because that column may have 3 ones, so all the rows corresponding to the 3 ones get eliminated, and in the reduced matrix, because of this elimination, some of the other rows may correspond to having a single one in that row. That will make some columns essential columns, and then you have to, by force you have to take them. So some of the exploration space do not remain flexible, or they become fixed. Okay, so that is what is being said over here, but in overall it becomes an exponential problem. So by using the heuristic I mentioned above, we try to reduce the complexity. Okay. So now it says that therefore, if you can determine that a given part of the search space does not contain any solution better than the one we have found so far, we can avoid exploring those parts and that search space altogether. That is actually the heuristic. So, okay. So, what is the heuristic saying? That if you can determine at a given part of the search space, that is a subtree rooted at a non-leaf node, okay, some other, that for example, it may have a lot of trees over here, but you are at the intermediate node, and if you explore down this path, there is no better solution than which you are currently having. So, it is better you can drop it altogether. Now, who can do that? Who can find out in a very quick time that exploring this subtree has no meaning? That is how heuristic will come into picture. Okay. So, that is what is the idea. Okay. So, so basically what the second point is saying in branch and bound algorithm. So, this algorithm is also called branch and bound algorithm, because we are branching and then we are finding out whether the branch has any good solution, then we again track back and try other spaces, other paths. Okay. So, we resort to two basic ideas: organize the search space in form of a binary search tree and explore the branches of the tree. And also you can say that I put a heuristic over here. Okay. What is the heuristic will do? Heuristic will find out which branch of the tree is not good, is not ideal, or it is not essential, or is not fruitful to explore, and then you try other parts. So, it is basically 3 parts: search space in form of a binary tree, explore the paths. These are the actually branch and bound algorithm, and complexity is very high. So, you put the heuristic over here, and the heuristic will tell you when which parts of the tree is not good to explore, so that you can branch and track back. Okay. So, that means what? So, now how you start off with this algorithm. Okay. So, what we do for efficiency, we need some scheme to estimate the lower bound of a solution without exploring in the tree. That is what is the heuristic. So, what will be the heuristic will do? So, heuristic is a scheme that will estimate the lower bound of a solution, that is the minimum this much amount you have to take, that is minimum this many amount of prime implicants you have to take without exploring the search space. That is very important. Without actually making the tree, you have to estimate that this is the minimum number of prime implicants required. That means the solution cannot go beyond this. Okay. So, because the solutions are very approximate, so you can have a somewhat a higher bound kind of a thing or a lower bound. Like for example, say minimum number of requirements will be say 3. So, that is the exact value. So, if you are using a heuristic, so sometimes you may land up into a case saying that the minimum number of requirement is 2 or minimum number of requirement is 1, something like that. Or sometimes if your heuristic is such, also you can say that your solution is coming that minimum number of requirement is 4 or something like that. So, some deltas will be there, and with that deltas you have to find out, you have to make, you have to work with this, because it will help you in not exploring some of the places, the paths. So, if we find that exploring a given path would lead to more expensive solution than expected, then we retract and some other branches in the tree. So, in other words, given a node of a search tree, we have selected and rejected some columns, right. So, in the root node, if you take a left path, that means you have not taken the node, you have taken a right path, you have taken the node. Okay, these columns are identified by the path from the root to that node. Okay. So, hence at a node we have a partial solution. The cost of the partial solution, if exceeds the expected value, clearly we can abandon the path and track back. So, what it is saying? So, actually at a root node, you say that you take left path and right path. Left path means you do not take it, right path means you take it. Next node means say you take this node. So, this will imply that you have taken the column corresponding to the root node. That means at each intermediate node you actually have a sub solution, that is you have taken prime implicant A, B, C, D and so forth, or you have taken prime implicant A, not taken prime implicant B and taken prime implicant C kind of a thing. Now, your estimator algorithm will tell you that after this subtree or starting from this from this node, which is not the root node, the subtree here, what will be the subtree here, this will be your subtree. So, what can be the minimum cost here? So, if you should add up this minimum cost for this subtree with the cost you have incurred till now, like for example, you have P1. So, if you take this node, that means you have taken already P1, that means your current weight is 1. Then you add up with the estimated value of the subtree here. So, if you add it with 1 and find out that the solution is so much, so if it is greater than the estimated cost or what your cost estimation you have, or it is better than or it is worse than your present solution, then you discard traversing this path and then you try to take this path into account, and this is how you progress. Okay. So, therefore, actually, so what we do, so in branch and bound essentially we will try different paths and each node will find out an estimate to find out whether the next solution is going to be good or not. If there is a possibility that the solution will be better than my current solution or better than my estimate or at least equal to my estimate, I will explore, otherwise I will not explore. Okay. So, branch and bound then tries to establish whether the best solution can still be found by proceeding from the current node in a different branch. That is when I have to progress to this other branch. Then again you have to apply the same thing. So, you say that you do not take this branch, take the other branch. Then again you have to repeat the algorithm by an estimator and find out whether can I get a solution at least which is better than which is the path which I have discarded. If not, then again you have to go by that discarded path, because this path is even more costlier than the other. Okay. So, now a very important part of this branch and bound solution, if you want to get a very quick answer, you need not go to the exponential complexity algorithm, then is the way of computing the lower bound depends on a particular problem. That is lower bound computation, that is your heuristic, which will tell you that the minimum this many number of prime implicants are required for the solution is a very important point in case of this solution or many other heuristics where you need to calculate a lower bound or an approximation, because many of the heuristics or many of the algorithm what you will do, you think of, because this branch and bound or proposing your solution, mapping your solution to binary tree or binary search tree is a very important paradigm which is used in many other places of engineering and computer science. But if you explore the whole tree, it will be the exponential complexity. Then you have to find out an algorithm which can estimate that what will be the minimum cost if you traverse this path. That is why this lower bound computation is very important. As well as it has to be as accurate as possible, and as well as it should be not a very exhaustive algorithm. I am sorry, it must be a very highly complex algorithm. You should be very fast to do this. So, the branch and bound algorithm should be this. The computation algorithm of the bound should be fast as well as it should be as accurate as possible. So, the branch and bound algorithm for unit covering problem generally so actually you know that these are all contradictory requirement like accurate estimation and it should be fast. So, they are all contradictory. So, therefore, the unit covering problem generally provides a near optimal solution, because this lower bound estimation heuristic execution time is low and obviously the accuracy is not very high. So, that is why your branch and bound will actually give a near optimal solution and it may not give you the exact best solution. But if you start exploring all the branches of the tree and go to an exponential algorithm, then obviously your solution will always be the most optimum, because again as I told you in ADCAD, I told you in the beginning, from the starting in almost every lecture I am saying that most of the design algorithms are actually the problems are exponential in nature, and here also we have proved that actually you can map the algorithm to a binary tree, so which is exploring is again 2 to the power n, where n is the number of nodes, or number of levels you can think, or number of prime implicants you can think. So, therefore, its complexity is 2 to the power n, and if your number of prime implicants is 100 or more than that, so you can never solve it in a practical time. Therefore, you are bringing in this lower bound computation heuristics, and that is why our solutions are going to be approximate. Okay. So, before we turn our attention to this computing this lower branch and bound, so let us just look at the branch and bound algorithm for the unit covering problem. In nutshell, let us see what are the steps we do. Okay, then we will see how exactly you can calculate the that lower bound. So, what you do, execute the lower bound computation algorithm. So, for the time being assume that there is a heuristic available which can tell you which is the minimum bound or which is the minimum, which tells you what is given a constraint matrix, what is the minimum number of nodes required to or prime implicants required to cover it. Okay, so, first you do is execute the lower bound computation algorithm on the constraint matrix and generate initial lower bound, which is the lower bound, and current cost is set to 0. So, you have first you are given a matrix, then you use this lower bound computation algorithm, and then you will find out what can be the minimum number of nodes required to implement it. So, it will give you a lower bound saying that 1 at least or 2 at least or 3 at least. So, again as I tell you, so lower bound algorithm in this case will not give you a higher estimate. So, that like for example, as I told you some time back that say for example 3 is the requirement of prime implicants to cover it. So, delta may be 4 or delta may be 2, 3, 1, but generally we will see that we will not go to the upper side, we will always go towards the lower side. Like if for example 3 implicants are enough to cover it, so we will not report 4, 5 or 6 in the delta side, rather we may report 3, 2, 1 and so forth. We may go down the lower side because it is lower bound. It is saying that minimum this many number of things are required. So, in the real sense it may actually from whatever bound you have got, it may slightly increase, but we will not go the other way, that we will not go for a higher side like 4, 5 or 6 and then our real algorithm or the exact algorithm will bring it down. So, we are not going to that because our computation is the heuristic is generating the lower bound, that is the minimum this much is required, we may even require more than that. Okay, so, initially you generate the lower bound on the total given matrix, after you do all the pre-processing, and then you say the current cost is 0. So, why the current cost is 0? The current cost is now 0 because we have not yet selected any of the prime implicants. Okay. Now, you select or deselect a column pi. That is what is first you go for this root node. So, that is in the solution space, if you take pi, so pi will be 1, else pi will be equal to 0. Okay. If the column is selected, then add pi to the cover and add 1 to the current cost. Obviously, as I told you here the weight of each of the prime implicant is taken as 1. Okay. So, now apply reduction techniques like essential row and all this to the constraint matrix. Okay. Now, you take a column. So, now we add 1 to it. So, arbitrarily you can start with any column, take it or reject it. But now, if you reject it obviously you have to do some pre-processing, we will see with an example. If you take it also you have to do a pre-processing. So, you have to take, if you take it you add a weight, if you do not take it, do not add a weight, and again pre-process the matrix and generate essential column, row dominance, column dominance and reduce the matrix. Okay. If all the essential columns, for all the essential columns add them to the cover and increase the correct cost. By doing the pre-processing, you find out that some of the columns become now essential. So, again add them to the current cost and again add them. Okay. If the problem is now reduced to a terminal case, if everything is over, so what you have done, you have taken one column, then you have done all the pre-processing, or you have not taken a column, any one of them you do. If you take a column, you select, you make the weight as 1, now you do pre-processing like essential columns you find out, row dominance, all those things you do, and for all the essential columns you have to take them and you have to increase the weight by adding 1 for each of the columns taken. Now, what you have to do? Now, if you find out that if it is a terminal case, that the cover is complete, then you have to find out what is the total cost. So, okay, if the total cost if the current cost is less than or equal to initial lower bound. Initial lower bound means that you have found out that approximately this is the minimum number of what you say that this means row columns required to cover the matrix. So, as I told you that this initial lower bound computation will always give you in the lower side, it will never give a result which is in the upper side. So, even if it is, I mean it can be some subtract delta, like for example, if in the real case the number of rows required, columns required will be say 4, so you can get the answer 3 or 2 or something like that, it will never be overshooting the result in the bound. So, if it happens that your current cost, that is by taking all the columns you have taken, is less than or equal to the initial lower bound, then you have got a very good case, then the lower bound is returned and the algorithm is terminated. So, because I told you this heuristic will never report anything in the plus side, it will always report in the negative side. So, for example, it says that 3 prime implicants are required to cover it and your current solution cost is 3, then obviously you have reached your solution, because you can never get anything less than 3, but in the practical case it may happen that you may require 4, 5 or 6. Okay, so if your algorithm is saying that the prime implicants you have covered till now is actually equal to or less than the initial bound, then your solution is done and you have reached a very good solution, you result it. Okay. But if it happens that on the reduced matrix, if it happens that this is not the case, that is your current cost is becoming larger than your lower bound, then obviously you have to try exploring. Okay. On the reduced matrix, again compute the lower bound, add the lower bound, that means what? Now, you have not reached the terminal case, or that is right. If you have reached the terminal case, then just check it. If it is greater than this one, then you can try exploring some other part. Okay, but if you find out that the terminal case has not been reached, then what you have to do? Then you have a reduced matrix. Further processing is to be there. Okay, on the reduced matrix, again compute the lower bound, add the lower bound to the current cost. Now actually we have again a new matrix has formed and it is not a terminal case. So again you apply a lower bound on that and add it to the current cost. So if you find out that, that means you are at an intermediate node, so that the cost is equal to 2. Okay, now there is one path over here, one path is 1. It is not yet terminal. Now you check that if I include this node on the reduced matrix, there is a reduced matrix over here and the reduced matrix over here. So there is a so this is the 2. So the current cost is 2. Okay, so now there can be two ways, you take it or you don't take it. Now here also you actually there will be a reduced matrix. That is after taking this node, we have reached here by saying that we have taken say node in this way, let us represent it in this way. So say this is a node over here and say you have reached this node by taking say some P1 you have taken and then you have P prime implicate 1 and 1 you have taken over here. So there can be two solutions, say this may corresponding to P2, you take P2 or you don't take P2, that is how you can explore. Okay, but at this point you have a reduced matrix. By taking P1 you have reduced, you have done rows dominance, column dominance, essential column, you have taken everything you have done and say finally you have got a reduced matrix and it is not a terminal case. Had it been the terminal case, you can find out by taking P1 and the essential columns what is the cost. If the cost is less than the lower bound estimate, then you are very good, you have reached the optimality and you can stop it. But if it is not the terminal case, then again on the reduced matrix you again apply the lower bound and see if the lower bound is say it is saying 3, that means in this reduced matrix you need at least 3 prime implicants to cover it. Then you add it to the current cost. Say current cost was say 1 over here. So 1 plus 3 is equal to 4. Now you have to check that whether this 4 is less than or equal to the initial bound. So if you find that it is greater than the initial bound, then you may know that even if I explore the place, minimum explore from this subtree, then it is minimum 3 you have to take to implement it, and 1 you are already adding, so the cost is 4, which is higher than my bound. So then you have to say that no, I do not want to take P1, I have to start taking the other path where I will not take P1. You will not take P1 and again you get a, so you will need another node over here, again it may correspond to P2, but now you have not taken P1, and this route you have covered. Now again you find out that in this reduced matrix by not taking P1, we will of course get another reduced matrix. And then again you find out what is the minimum lower bound in the reduced matrix, then you add it to the current cost. In this case obviously current cost will be 0 because P1 you have not taken. Okay, then if you find out that is lower than your initial lower bound, then there can be a possibility that if you explore this path you can get a good solution and start exploring the path. So this is what is as being actually you are saying. So if there is this value is lower than the current cost, then still there is a chance of getting an optimal solution. Identify the column to be selected, deselected from the reduced matrix and go to step 2 and you reiterate. Okay, if the value of current value plus current cost is higher than the initial lower bound, then there is no point in exploring that path. Undo the selection, that is what I have said. You undo P1 in our example, as I was saying, undo the selection of the column done in the last step and consequent selection and deselection, that is you undo everything, that you do not take P1 and then after by taking P1 or not taking P1 you have done some matrix reduction, again undo everything and actually you go to step 2 and traverse another path by selecting or deselecting a column. So essentially what we have done actually, we have taken the matrix, we have selected a solution or deselected a solution. First we have found out what can be the initial lower bound. Then we take a column or we select a column or do not select a column. Based on that, if you select a column you add a weight to 1. Then you reduce the matrix by your dominance, equivalence and essential columns. If you take some essential columns, you add it to the weight. Now in the reduced matrix again you apply the approximation lower bound computation. Then you add it to the current cost. If the current cost after addition is lower than your initial estimate, then you say that it is profitable to explore that path, you do it, and if it is not, if the value is higher than the initial estimate, then you discard it path. And what do you mean by discard the path? You go back to step 2, you undo everything. Undo means if you have taken column 1, you do not take column 1, or if you have not taken column 1, you take column 1 and some matrix reduction you have done, all this you have to undo and start again exploring another path. And you keep on doing it till you find out a path where your solution is equal to or less than your initial current bound. You keep on doing it, so you can find out. Now where is that approximate part here? Because some of the points you are using a lower bound computation. Okay, so lower bound is you will find out is a heuristic algorithm, and always it may not give you the very correct solution. So if it is not giving you the correct exact bound, so at some of the paths you may leave, saying that it is saying that the lower bound is 2, but in fact if you so you may be very much attracted by saying that okay, it is saying that the lower bound is 2, to find it out. So, you can start exploring the path, but when you will be going towards the path, you will find that the lower cost is actually 7 or 8 or something like that. It may happen like this, because the lower bound in these algorithms are very tight. So, it will never give you an additional value, the delta will be always negative. So, you can find out that it is being it is saying that this path or this exploring this subtree can give you a solution with cost of 3 prime implicants. So, you are prone to explore that path, but in the end you will find out by exploring that the cost is 5 and 4, 5 or 6 or something like that. So, that was not a very good idea to explore the path. And similarly, for some of the paths it has reported a 2, but in fact if you really explore the path, the value will be 2 only or 3, maximum 1 delta will be there. So, you could have explored that path and you could have got the better solution, but because of this heuristic, you may land up in going in a path which was showing that it is going to get the value of 3, but the delta has become plus 4 or plus 5, and so you have gone to a different bad direction and you are getting a solution which is higher in size. So, all these things may happen. Okay. So, now we will see how can you compute the lower bound. So, the algorithm is pretty simple. Start exploring. At every intermediate step, use the lower bound computation tool and find out what is the value, add it to the current cost. If you find out that this path is good exploring, explore it, else you undo the path and try other path. But the very simple algorithm will follow, and that is actually branch and bound algorithm with the heuristic. Now, we will see how some heuristic we will see how to compute the lower bound, because in this branch and bound algorithm, which is very straightforward and simple, the heart of this algorithm is the how accurately you compute the lower bound. So, if the lower bound is a very accurate algorithm, your solution will be better, and if your lower bound estimator is not good, your solution will not be that good. Okay. So, before we do that, some definitions are there. Let us give some definition. So, given a covering matrix, that is your constant matrix or whatever, suppose two rows have non-zero columns in common, we say the rows are independent or column disjoint. That is, say for example, in one row you have 1 1 0 0 and in the second row you have 0 0 1 1. That means these rows have no 1 places in common. That means, so this is P1, this is P2, this is P3, this is P4. So, then it means what? To cover this row you need either P1 and P2, and to cover the second row you require either P3 and P4. Okay. So, if this happens, so what is the case? That these two rows are column independent, that is or column disjoint, that is 0 1 1 0. So, this is row 1, this is row 2. So, again you see, to cover row 1 you require this column, and to cover row 2 you require this column. So, that means they are column disjoint, that is there is no common column which is having 1 in both the cases. So, if you have, so more the number of column disjoint rows, more number of prime implicants has to be taken. So, obviously you require 2 different columns to cover these rows, obvious. So, in a general argument, if a matrix has n rows that are disjoint pairwise, you require at least n columns to cover the whole matrix, fine, that is obvious. So, in this case rows are said to be independent set of rows, that means each of the row is involved his own prime implicant, so or a column, so they are independent of each other. So, in the constant matrix given below, correspondingly you will see that this is your some matrix is over there. So, what you can find out that is being said. So, in the constant matrix given below, rows corresponding to mean term 1, mean term 3 and mean term 5 are independent, and so are 2, 4 and 6. Okay. So, in this case if you see this, so you can see that row number 1 if you take, so if you take this row number 1 you just consider. So, this row you consider and row number 3 you consider, you can see that it does not have anything in common, ones in common. So, this one has row 3 has ones in 2 and 3, row 1 has 1 in 1 and 6, and row number 6 has a 1, 3 and 5, 1, 3 and 5 if you take. So, in 5 if you just find out, so it has a 1 in place of 4 and 5, excuse me. So, that is what. So, if you have to cover mean term 1, 3 and 5, 3 columns will be required. So, for example, if you take Pi 1, it will come mean term 2, if you take Pi 2, it will cover mean term 3, and if you take mean term 5, you have to take mean term 4. So, in these other words, so 1, 3 and 5 are all column disjoint rows or independent rows. Similarly, if you take mean term 2, mean term 4 and mean term 6, you can find out that there will be no single column which is having a common 1 for any 3 of these rows. So, if for covering this mean term 2, you should have taken either Pi 2 or 1, mean term 4 you have to take 3 or 4, and for mean term 6 you have to take 5 or 6. So, 3 rows will be required, 3 columns will be required to cover 2, 4 or 6, and again 3 will be required to cover 1, 3 and 5. So, of course, these 3 are 2 independent sets, 1, 3 and 5 and 2, 4 and 6. So, between these 2 sets there can be obviously some overlap, but if you consider 1, 3 and 5, 3 are required, and for 2, 4 and 6 again 3 columns will be required, but between these 2 subsets some common stuff will be there, but by looking at this matrix you can easily say that the lower bound is 3. Because there are 3 independent column independent rows, so each will involve 1 prime implicant. So, the lower involved will be 2. So, that is what is being said. So, we need at least 3 columns to cover the matrix. So, lower bound is 3 in this case. right. For cyclic matrix, lower bound is 2. So, how is that? So, how do you get a lower bound? Because nobody can give you a solution in less than 3. It can be more. Nobody is saying that it can be exactly 3, but nobody can give you a solution less than 3. In a cyclic matrix, what is a cyclic matrix? So, we have seen a cyclic matrix is something like 1, sorry, you can think just in the last class we have seen some example of a cyclic matrix. So, cyclic matrix is something like, you just remember what is a cyclic matrix. There will be always 2 ones. So, there will be no, you cannot reduce the matrix further, like if you can see this one, this one, this one and this one. So, this matrix cannot be reduced. So, it is a cyclic matrix. So, obviously, you know that nobody can solve it in a single column, because there is no reduction possible, there is no column with all ones. Okay, so, at least what is the lower bound? The lower bound is 1 plus 1, that is equal to 2. Okay, because in such a matrix there is no reduction possible. Secondly, there is no single column with all ones. So, obviously, the lower bound is 2, but it does not mean that you can get the solution in 2. It says that nobody can find out a solution which is less than 2 columns. Why? Because there is no row which is having all ones. So, that means at least 1 plus 1 you have to do, and 1 plus 1 plus how much I am not saying, but it is saying 1 plus 1, that is minimum 2 rows will be required, sorry, 2 columns will be required, and further the matrix cannot be simplified. So, for all cyclic matrices, so what it is saying, for all the cyclic matrices, so the lower bound is 2. Okay. So, that is what is the theorem saying, the lower bound of a cyclic matrix is 2. Now, why is it? So, now there is only one case where the lower bound is 1. So, now we can just, we are again proving it by contrapositivity. So, if I say that the lower bound is 1, so the lower bound is 1 means that is somebody should be able to find out a solution in one column. So, one column solution means the matrix contains a full column of ones. So, as if it is a full column of ones, then it is not a cyclic matrix, and cyclic matrix is a case which I have already shown in the last slide. So, it has some ones, but there is no column with all ones, and obviously matrix cannot be reduced. So, minimum 2 columns will be required to solve the problem. So, that is why we say that the column least cost in this case, so the lower bound is 2. So, that is therefore, the matrix is not a cyclic matrix if the lower bound is actually 1. So, lower bound is 2 means 2 plus. So, nobody can give a solution less than 2, you have to add something. Okay. So, these are some of the theorems. Okay. So, now we are going to see for a heuristic for computing the lower bound. So, again it will not give you a very accurate solution, but it will give you some solution. So, what is it is saying that add a field w to each row which is equal to the number of ones in that row. Okay. Choose the row with minimum number of ones, choose the minimum number of ones, that is minimum weight w, let it ri. So, if there are multiple values with same value, choose the one from the top. So, what we are doing for each of these rows, we are adding a new counter which is the number of ones in that row, and then we are arranging it in an ascending order. Okay. We are arranging it in an ascending order, and then what you do, we start taking from the top. Okay. Delete all rows rj. Okay. So, rj such that rj and I have at least one row in column, one row in common, we also delete rj. So, what we are doing, say this ri, see this row with the smallest number of ones. Okay. So, we first delete this row, and then if you and if there is some common ones in between some other row like rj. So, there is a one common over here in one rj, say. Okay. This is rj. So, there is another row, we will see with an example. So, there is another rj is there. So, it is a common one with there, another rj say. Okay, it is a common with 1 at this point. So, you delete ri, along with them also you delete the rj's. Okay, so, repeat these two until no more rows remain. Okay, so, how many times you have selected r2, sorry ri, that is actually your lower bound. Okay. So, now we will see with an example that is better, then we will again come back. Okay, then we will see what is the motivation. This one tells that what is the motivation of such a heuristic. Okay, so, in this case you see w is equal to 2 because there are 2 ones in this row. Okay. So, here also it is 1, 2, 3. So, you have written as 3, 1, 1. So, you have written 2 and so forth. Okay. So, in this case these are the weights. So, now this is the least weight 2. So, we start off there some other like 1, 2, 3, 1, 2, 3, 4 rows are having weight of 2. But again as I told you, we start from the top. So, this is the case, right. So, now this is the what you have said. So, now you eliminate this. So, you say that my value lower bound is 1. Now, what you have to do? You have to again this was this 1 and called row 1 and 2 had a same 1 is a common. So, again you reduce 2. Okay. Then again this it has a common with this one. So, again you reduce this one, right. So, any more commonality? I do not think there is any more commonality over here. So, yeah. So, these two rows are now reduced. Okay. So, now you are saying that you have taken on, you added only 1 and row number 2 and row number 4 gets deleted. Okay. Now, next what we do? Sorry. Now, let us see. So, now this is done. So, if you now you are kept with this matrix. So, if you are you have kept with this You can think about this reduced matrix you are having. Okay, now again you take with this third row. Okay, third row again. So what you are seeing that you can see that this row you delete, row number 3. So again you add a 1 over here. So if you are deleting row number 3, so what is the commonalities you are having? So it has 2 rows. So it has a common. So again row number 3, so you have deleted, so you are having a common of, so you have taken this row, you have taken this row. So there is a common with the 6th, which is all with a 6, so 6 also you can delete. Okay, so because this one is having a common with this one, so this is gone. Again you take this one. Okay, it has a common with this one, so this one is gone. Okay, and there is no more this one. Okay, so the lower bound is 2 and it comprises 1 and 3. Okay. So, let us quickly see what we have done. So, again you just see, so we started this weight, we started 2. So, this one is having a common with this one, so this can be eliminated. Okay. This one is having a common with this one, so 4 gets eliminated, and any more commons? No. Okay. Then actually you add this one. Now, this row is added. Okay. Now, what you do? Now, you take, this is the least row. So, you take 2. So, there is a common of this guy. So, this guy is eliminated. Again this one is having a common with this one. So, this guy get eliminated, and 1 and 3 is remaining. Okay, these 2 have included. So, the cost here is 2, that is the lower bound is 2. So, these are a way of saying that if you take this matrix, nobody can solve you or give you a solution in less than 2 prime implicants. So, this is the idea. So, now let us see what is the heuristic. This is a heuristic. So, what is the motivation between this? So, the motivation actually is written in this slide. Motivation is written in this slide. Okay, and then we will see, I mean what we have done, and then what we will see that. Now, again we will come back and explain. So, what is the motivation? The motivation says that why we have given our weights. So, we said that the minimum weight is 2 or minimum weight is 1. That means what? This row will be covered by the minimum number of columns. So, to include this or that is more, it is more difficult to get this included compared to this one, because this row 2 is covered by 3 prime implicants. So, there is a higher probability of selecting this row or covering this row by if you are selecting the prime implicants and some order. But here the number is only 2, or if some number is only 1. So, if there is only one in the row, you know that it becomes an essential prime implicant. So, less the number of ones in a row, more difficult it is to be covered, or less the probability to get it covered, or more difficult it is. We should not call it probability, because all the rows has to be covered, but the idea is that it may be very difficult to cover that row compared to a row which has all ones or more number of ones. So, that is why we do this ordering, and then we start with this one. Then we take the first row with a what you say that we say that we select this row. Then how do you select this row? So, we select this row, it may be either selected by this one or it may be selected by this one. And why we have started with a minimum number of ones? Because that is more difficult to be covered compared to the other case where there are more number of ones. So, it is done. Now, you say that if the row number 1 is covered by Pi 1, then automatically mean term 2 gets covered, right? And if you cover it by Pi 5, so again this mean term 4 gets covered. So, that means it is saying that if you take row 1, then there is a very high chance that mean term 2 or mean term 4 will be covered. So, it is actually cutting out this 2. Now, here is a problem. So, you are quickly reducing the matrix, but in essential what will happen? You will cover mean term 1 either by Pi 1 or by Pi 5, but not both. So, in this case there is a choice that if you cover by Pi 1, then you can eliminate mean term 2 or row 2, and if you cover by this is row 2 can be eliminated, and if I use Pi 5, then you can eliminate row number 4. Then you can eliminate row number 4 can be eliminated or this, but not both. But if you do this, then again you are doing a tree. So, if I again thinking this if then else question, like if I cover mean term 1 by Py 1, then you remove R2 row 2, or if I do it by Pi 5, then you remove by 5, then the heuristic and again a tree is coming into picture. But we do not want to do that. What do we want to do? We want to do is that we want to go for a very quick solution. So, in this case we say that it will be covered either by Pi 1 or Pi 5, but not both. But if so, there is a good chance that this will be covered and this will be covered. Similarly, now we take 3. So, if we take the row 3, so this one is if you do by Pi 2, so you can easily cut mean term 6. If you do by Pi 3, you can cut mean term 5, but not both. But in this case, we will cut both the rows because it is a heuristic and we are going to give you a lower bound. It is saying that if we cover mean term 3 by Pi 2, there is a good chance that 6 will go, and if you do it by Pi 3, there is a very good chance that row 5 will go. Okay, but not both. But as is a heuristic, we are going to cut out our solution very fast. So, we are just saying that there is a probability that if you take mean term 1, if you cover mean term 1 by Pi 1, then or you just do not say anything, you just say that if the first row is covered, then there is a good chance of covering mean term 2 or say mean term 4 directly. min term 4 directly. So, we cut out both of them, and there is a, so the speed is coming in the algorithm because we are reducing more and more number of rows in iteration, and there is no if then else condition. So, you are quickly going to get a lower bound. Obviously, you see that you are going to get a lower bound, but not any positive delta. Why no positive delta is there? Because you are saying that I am taking this, covering this row by pi1, and automatically another row gets covered. But the idea is that by 1 you can either eliminate row 2 or you can eliminate not 4, but not both. That is very much clear over here. If you take pi1, so you can cover min term 1 and min term 2, and if you take by pi say 5, then you cover min term 1 and min term 4, but both of them is not going to happen. But in the heuristic you are saying that in one go I am covering min term 1, min term 2 and min term 4. So, you are taking more number into picture, so you are going to get the lower bound to the downside, to the negative side, not to the upper side. And we explicitly want to do that because we want to get a very faster solution, that is quickly going to reduce the number of matrix sizes, and that is actually going to give you a good solution. I mean, I am sorry, I am going to give a fast solution, but the bound will be toward the negative side. So, the real solution, the answer will be higher than the bound I am going to get, and that is how your heuristic is designed, or your branch and bound with heuristic is designed. So, if you can reach the, so that means what? So, whatever this algorithm will give you is this one. Okay, and this is the real solution can be here, or the real solution can be here. This is the heuristic solution. So, real solution can be above this, and the real solution can be also at the level of the heuristic, but it will never be down this one. So, now, so that is what is a good side. So, if you somehow get your solution, that is by you are doing branch and bound, and for some solution you are doing. So, if you find out that it is actually reaching the value which you have got by your heuristic, so you know that my solution is the most optimal one, because I cannot go beyond that one. That is because this heuristic is going to give you a solution which is at least the lower bound, and it may go up, but nobody can give you a solution in less than that value. So, if you are doing a branch and bound, and if you are going to reach the value which is given by the heuristic, so you know that you have reached the solution where nobody can give a very less value than this one. So, this is how the heuristic is explicitly designed. So, you can easily ask, that is why I told you can easily ask the question, but you are saying that if I take min term 1, so I cover min term 2 also and min term 4 also. How is it possible? The possibility is because it says that nobody can do any less than that, but nobody is claiming that you can do, you need not take any more than what this heuristic is suggesting. Okay, so that is why some inaccuracies are there. Okay, so the basic motivation is taking the shortest row is that because because shorter the row, higher is the probability of involving in a cover in it, or in other words, more difficult is to be selected. So, in other words, what I say that the shortest row, that is minimum number of ones. So, if a row has minimum number of one means, that means what? It is going to become a essential prime implicant, and the column corresponding to that will has to be included. So, you have to give some good priority to selecting of that row, that is what I have told you, but it also led to an inaccuracy. So, a very simple example is there, let row 1 be selected to be deleted. Okay. So, that can be a case. Let row 2 has a common column, let row 2 has a common as column 1 with row 1, and row 3 has a common column as row 2 with common 2. Just read this paragraph and do this, you can easily find that it will happen. So, it is saying that let row 1 be selected to be deleted. Let row 2 has a comma. So, this is row 1. So, sorry, let us do this. This is row 1. Okay, this is row 1, this is row 2, and this is row 3. This is 1, 2, and 3. Okay. So, now it is saying that let row 2 has a common as column 1 with row 1. So, this is both of them has a 1. Okay, these are column with 1, and row 3 has a row 3 has a common as column 2 with row 1. So, in this case it is a 1, this is a 1, and this is a 0 kind of a thing, and this is also a 0 kind of a thing. So, the lower bound estimate in this case is a 1. Okay. So, how is that? So, here the weight is 2, it is a 1, and it is a 1. Okay. So, now if you take in this case okay. So, this is how it will look like, and now if you find out this whole algorithm that which I have discussed, so you can find out that in this case the lower order algorithm will be equal to 1. So, how is that? Let us see. So, we have taken row 1 is selected to be deleted. So, how this is, sorry, so you just represent it this way, just I will write it in a different way and nicely you will find out. So, let us just read from this one. Row 2 has a common as column 1 with row 1. Okay. So, say this is row 1, again row, we will take a blank sheet. I am just sorry about it. Okay, we'll just to get this point. So I mean, giving a direct example at this point in this case is going to be redundant. So we'll just remember this point, and we'll again come back to this slide with this example. So this part, that how this solution is going to give you a wrong estimate. So we'll see that. Okay, so this one will come back to this point later. So just it just tells that because of this heuristic we have taken, so sometimes you may get a wrong value. So how this will be there, we'll take an example and then again we'll come back to this point. Okay. So this is the example we are talking about, and now so this same example will show that sometimes you are going to get a wrong value in this estimate. Okay, so let us just go back and go to the forward, and in this case. So this is the matrix. So this is our working example, and this will be used by us for illustrating the theory. So if you look at this, so this is a very big matrix. So I am not going to solve it. In this lecture, so you can easily do that. So if you find out the lower bound estimation algorithm in this case, so you will find out the lower bound is equal to 4, that is will be equal to 1, 3, 5 and 7. So if you just put up the weights and you can do that, you will find it out. Okay. So 1, 3, 5, 7 is your answer. So that means the lower bound is 4. So in the first step of an algorithm, lower bound says that these are 4, that means nobody can give a solution in less than 4. So that just you have to keep it in mind. Now if you are doing branch and bound, and you are finding, and you find out that this is 4, so now you are doing a branch and bound, and if your solution at present is somebody saying that is equal to 4, then you should be very happy that you have reached the solution. Now what we do? So again we start exploring. Now you have to start doing it. So, okay, so we start exploring solution space. Let us start with PI1. This is the case. So also you can see that in this case you will find out that at present there cannot be any pre-processing done. There will be no essential column, no essential row. Sorry, no essential row will be there. So there is no singleton, and you can find out there is nothing is dominated or being dominated by row dominance and column dominance. Nothing of what you can say simplification can be possible in this matrix as of now. So now we start exploring solution space. You take PI1. Okay. So what do? You take PI1. So if I take PI1, so automatically this row will be covered. Okay. Again PI1 mean term 3 will be covered. So let us very in a nice way remove this, because I have taken P1. So this is also eliminated, and again mean term 12 is eliminated because I have taken this one. So this is your this number is there. Now you can see that if in this way what happens. So this is what is I have taken. So automatically by PI1 mean term 1, mean term 4 and mean term 12 gets covered, correct? Now you have to just see what happens if there is a now what are the repercussions for that. Rows 1, 4 and 12 are covered. Column PI2 and PI4 are dominated. Just see PI4 and what is saying that PI2 and PI4 are dominated. PI2. So you just see PI2 has a 1 and this PI3 has 2 1s in this place. Okay. Similarly for PI3 it is a 1, so and no other ones in this column and no other ones in this column. So obviously this PI3 is dominating PI2 and PI4. So by that rule you can eliminate this, you can eliminate this. So these two rows get, these two columns get eliminated by because of this dominance by PI3. Next, what is the case? PI3 becomes an essential. Okay, why is that? Because you see now column row 3, if you see there is only one in this, so PI3 becomes a essential, this one, because in this case because PI2 is dominated by PI3 and again PI4 is also dominated by PI3. So now you can eliminate PI2 and PI4 and you have only two, what do you say, this numbers, this PI3s are 2 1s are there. So obviously, and if you look at this this mean term 3, so you can only see that there is only a 1 in the row because they are all eliminated. So you just see that there is only 1 is there in this whole row. So obviously PI3 becomes essential. So if PI3 becomes essential, you have to take this, so automatically mean term 2 gets covered by this one and mean term 3 gets covered by this one. So our current solution is what? You have taken PI1, automatically PI2 and PI4 gets covered. So your cost is, initial cost is now 2 because PI1 and PI3 is there. So now obviously mean term 2 is gone, mean term 3 is also covered by this one, and any more ones over here? No. So now your PI3 is obviously taken into picture. So this is the PI3 has already been taken. Now we will find out that you have got a simplified matrix as this one. So it is 5, 6, 7, 8, 9, 10, 11 and this one is your matrix, and you have taken PI1 and PI3. So this is the first step of the branch and bound algorithm. Cost is 2, 1 plus 1, 2, and we know the lower bound is 4, that you can easily find out by using this algorithm. So this is what is the structure. So now we have reached this space. So now what is the case? So it says that, so in this case the thick lines, I am sorry, it is drawn in a reverse way. So in this case the left edge, the right dotted lines indicates the column being taken and not being taken. So, this one actually so this one corresponds to being taken and this one corresponds not being taken. So, as I told you that generally sometimes we write this left edge as being not being taken, this is not being taken and this is being taken, we generally write, but in this case they are representing by dotted line and thick lines. Okay. So, what it says that Pi1 is taken obviously, and then Pi3 default comes into picture because it becomes the essentiality, and Pi2 and Pi4 gets deleted because of the column dominance. Okay. So, that is being represented by this part of the tree. Okay. So, now this is the case. So, the left edge indicates that P1 is taken, okay, and this one indicates that Pi is taken because of taking Pi1, Pi3 has become become essential and it has to be taken, and Pi3 and Pi4 gets eliminated because of the row and column dominance, because of the row dominance. So, this is what is being represented over here. Now, this is your reduced matrix. Now, what do you do? Again you have to apply the minimum bound algorithm. So, if you again apply the minimum bound algorithm, you will find out that the cost of the solution, now the intermediate cost is now 2 because you have taken Pi1 and Pi3. So, that is the thing, and this is the reduced matrix. Again you have to apply now what? You have to again do a lower bound computation on that. Okay. So, now if you do a lower bound computation, in this case you will find out that 5 and 7. So, if you take 5, so these are all gone, okay, and if you take 7, okay, if you take 7 in this case, so this one is gone, and what else? 7, this one is gone, this one is gone. So, you can find out that by taking 5 and 7, this 5 and 7, you can find out the whole matrix will be covered. So, in this case the lower cost is nothing but this is the lower bound for this algorithm, which is 2 comprising of columns 5 and rows 5 and 7, the lower bound is 2. So, you have to add it to 2, the present cost is 2 because of column number 1 and column number 3 it is 2. So, you add 2 to the lower bound of this. So, 2 plus 2 is equal to 4. So, now this 4 is equal to the initial upper bound computation, initial lower bound computation. So, initial lower bound computation was equal to 4. So, we now can understand that is what. So, if you explore this path, so there is a chance that if you explore this path or explore from this area, so these are led to this matrix. So, the cost is equal to 2, then 2 plus 2, this 2 because of Pi3 and Py1, so that is equal to 4, which is actually equal to the lower bound. So, it is a good, so it indicates that there is a good chance that if you start exploring this path, you may get a solution which is equal to 4, okay, or 5 or something like that, but at least there is a possibility that you get the solution which is equal to 4, and if it happens, then you are in a good shape because nobody can give you a solution in less than 4 for this matrix that has already been proved. Okay. So, now again what you do? So, again you eliminate, now you will be starting working on this matrix because it has given you a good lower bound, has said that it is very good, you can explore on this matrix, and then you may get a solution of equal to 4. Now, what you do? Rows, okay, let us now consider column 5. Now, Pi5 is being taken. So, you are trying this way. So, Pi5 that is being taken. So, you are going by this path. So, let us assume that they are taking the point 5 is being taken and we are exploring this path. Now, why we are exploring in this path? We are exploring in this path because this matrix has a lower bound 2 and there is a good chance of finding a solution. So, let us take Pi5. So, if Pi5 is taken, so min term 5 is covered, min term 9 is covered, min term 10 is covered, and min term 11 is covered. Okay. So, that is a very good thing. Now, if you see, our reduced matrix will be what? So, our reduced matrix is now this portion, right. So, this is our reduced matrix. Now, if you see our reduced matrix, what is the case? So, if there is any there is singleton. So, now what happens? You see, so with 5 being taken, the following happens: row number 9, 10 and 11 are covered, right. Say 5 is taken, 9, 10, 11 are automatically covered. Columns 9, 10 and 11 are all dominated by 6. Okay. So, now you can check 9. So, there is only a 1 here, 9. Then they have said what is the case? 9, 6, 9, 10 and 11. If you take 9, this is 10 and this one is 11. So, you can see they are all 9 will be dominated by column number 7, I think, Pi6. So, if you look at Pi6, it is having a 1 over here and it is having a 1 over here. So, it is obviously dominating this column number 9. Similarly, column number 10 also you can see there is a 1 over here, in Pi6 is a 1 over here and extra 1 over here. So, again Pi10 is dominated by Pi6. Even for Pi11 you can see there is a 1 over here, there is a 1 over here and there is extra 1 over here in Pi6. So, Pi6 is dominating 9 and 10. So, obviously, this 9, 10, 11 and 9 will get eliminated. So, 9, 10 and 11 will be eliminated by this one, and finally you are having a matrix of this size. So, this one is also reduced, not there, and so obvious P1 you have taken. So, it is very small matrix size. This one is left behind, having this one only, this sub part only. So, this one is actually this one, you can see 6, 7, 8, 9, this one. So, now where we are, from the left edge of the node Pi5 has been taken. So, now you can see that in this case Pi5 has been taken. So, 9, 10 and 11 all are primes over here, because they get eliminated by the dominance rule. So, now we are at this case. Okay, so, now we are at this case. Now, there is a question that again this is the reduced matrix. So, again you have to apply what? You have to apply the lower bound algorithm on this one. Okay. So, now from this one is being taken, that indicate this one is the case, the left edge node marked Pi5 has been taken in the tree. Also in the edge it is marked, these are all primes, indicate that these are taking Pi5 and Pi9. Okay, actually taking Pi5, it says that if you consider Pi5 eliminates this 3. So, that is been actually is represented by this part. Okay. So, now we have done. Now, the reduced matrix is this one. Now, again you have to apply the lower bound computation in this. Okay. So, now what is the minimum cost now? The minimum cost is now 3, Pi1, Pi3 and Pi5. Okay. And now you have to find out the lower cost, lower bound, and you have to add to this one. Now, in this matrix the lower bound is 1. Just let us see what does that mean. So, in this case if you just put the weights, so in this case the weight is 2, this case weight is 2, and this case the weight is 2. Okay, now you just consider this one. So, if you take this, so this node, this will be getting covered, and this 2 has a common, so this one will be getting covered. So, it says that the lower bound is only 1. But in fact, you can easily observe that nobody can give you a solution in 1. The answer is always 2. So, if you consider, you can take Pi6, Pi7, then it will all be covered. You can take Pi7 or Pi8 with a cyclic matrix. So, the bound is actually 2. Okay, but if you take the lower bound as heuristic which you have taken, so in this case what happens, it is saying that the weight is 2, the weight is 2 and this weight is 2. So, you just say take Pi6, correct, and then if you take Pi6, this one will be covered by virtue of this. So, this is a common one, this will come and one. This is where the inaccuracy comes into picture, and this actually whatever I have shown by this matrix is actually stated in this statement which we have this one. So, this leads to the inaccuracy. That why this leads to the inaccuracy, the example I have told over is this one. Just read that this paragraph actually states what is being happening in this case. So, it is saying that the requirement is 1, but in fact when can the lower bound be 1? The lower bound can be 1 only when there is a column having all the numbers as 1. So, if it is not the case, but still your heuristic will tell you that in this case the lower bound is 1, because in this simple heuristic is simple. So, they have not given a factor that to check that if there is, whenever you are generating the solution of lower bound is 1, nobody is checking that whether really it is the case. They are not checking it. So, what they are doing it? They are saying that the lower bound is just by following the weights and doing the reduction. So, whatever you get, you do. They are not putting an extra check to find out, if really the lower bound is 1 or nobody can anybody give a solution in 1, that is not being checked. All these things are there because you have to make the algorithm go fast and quickly you have to get the estimate. That is what is the idea. So, this one will give you a bound of 1. Okay, so, now what is the present solution cost? Pi1, Pi3, Pi3. Then it will say the lower bound is 1. So, you add 1 and then you find out that yes, the answer is 4. So, in this 3 plus 1 is 4, that is very good. So, you can still, they are still giving you a hope that you can find out this one. So, now you are at this stage of the tree. Now, you are here. So, you were given the matrix. So, it has generated the cost of 1. So, now your present cost was Pi1, Pi3. Okay. So, 2 plus Pi5 you have taken 1, 2 and Pi1, Pi5 you have taken, and also I think you have considered Pi6. Pi1, Pi3, Pi5. So, 3 values you have taken. So, Pi1, Pi3 and Pi5, 3 mean terms prime implicants you have taken. So, the cost was 3, and here the intermediate matrix, that is small matrix, cost was 1. So, you are actually adding a value of 1 over here, that is equal to 4, that is equal to the lower bound. So, there is a hope that you can explore in this path. Now, what can be the exploring in the path? So, you can say that I can take Pi6 as 1. So, that is the case. So, you are taking Pi6 as 1. So, you are going by this path. So, if you can see, if I take Pi6, so you are actually covering this guy, you are actually covering this guy. So, automatically, this will be eliminated and this will be eliminated. Okay. Now, what happens? By default, so you are actually coming over here. Now, you have, so Pi6 you have taken, you have come over here. So now, or if you consider this, so now what happens by default, so you have taken this, now default this one is taken. So now in this case Pi6 is there, so now there is a choice whether you will take Pi7 or Pi8. So again a choice is there, because by taking Pi6 min term 6 and min term 8 has been covered, now remaining is min term 7. So any one of them you have to do by considering Pi7 or Pi8. Okay, now if you do that, so this is your path, so you can take Pi8 or you may not take Pi8. So if you take just if you consider Pi, so Pi6 you have taken and Pi7 you have taken, this is the case. So let us go back and see. So you have taken Pi6, now you also consider Pi7. So that is the path. So then everything is covered and you are done. Okay. So Pi6 you have taken, both of them are covered. Pi7 if you take, again min term is covered. So this one is the case. So it's a terminal case here. So you may not even explore this part, you may not even explore. So Pi6 you have taken and Pi7 you have taken. So this is the path, this is the terminal case. So I am sorry, this is a terminal case over here. So it says that Pi1 you have taken, Pi3 becomes essential. This is the case, you have come down. So at this stage you have found the matrix, the cost was 1, lower bound 3 plus 1 4. So you explore it, you take Pi6. This is the case, you take Pi7. So now the cost is equal to 5. So 1, 2, 3, 4 and 5. So the cost is 5, that is more than equal to 4. That means what has happened? That means your this lower bound computation has misguided you. It has said that this matrix cost is 1. So you have said that it's very good, let me explore. So you have started exploring this path, you have taken Pi6, then you have taken Pi7, then you have found out a terminal case where everything is covered, but the cost coming is now 5. Now you have to backtrack. So how you can backtrack? You can go here and say that I don't want to consider 6. Now and undo everything. So you undo everything means you have to come again to this picture and then you undo. You don't take Pi6. You start by taking, in this case you don't take Pi6. Then you actually come over here. You don't take this one. This row is no longer there. So now what you have to do? Now you have to cover all this. So you find out that you have to either take Pi7 and Pi8, both of them you have to cover. Because I mean this is a cyclic matrix, so you can easily see that if I take Pi1, these two will be covered, and if I take Pi1, this will be covered. So obviously both of them has to be covered. So you are in this situation, Pi7 and Pi8, both of them you have to cover. So again the cost is 1, 2, then 3, 4 and 5. So again the cost is 5. So that means here you actually landed into a problem. Sorry, so this where it is saying that the cost is equal to 4, sorry, the cost is equal to 2 is in fact a false one. So in fact this one said that the cost is 2, you can explore, we explored there, and then we find out that sorry, it said that the cost is 1, so we explored there. So it says that the minimum cost of this matrix is 1, so we explored this part of the subtree. So this part of the subtree we explored, so this is the part of the subtree we explored and found out that this is not the fact. Every time the cost is being 2 over here, so the total cost is becoming 5, which is higher than the initial bound. So we have reached a problem. So now what we have to do, we have to again go back to this node and again you have to try, because now we are in the assuming the fact that this was actually telling this second matrix, it was saying that the cost is equal to 2. In fact was wrong. So there is some problem over this. So you have to try with some other node by not taking now Pi5. So initially we started here by taking Pi5 and doing all the computations. So now there can be another path by this one which is not taking 5. Now you can explore on the whole tree, you will find out, but everywhere you will find out the cost is equal to 5. So this is a case of an example. So I have illustrated the whole theory with an example, but here there is a big problem that has come, that is you explore the whole tree, you had to explore the whole tree. So these are terminal, like for example, if you just read through the slide. So in this, this is a terminal case. So whatever I told you. So these are some of the, this was a terminal case. This was another terminal case. So all these things are written over here. So this one terminal case is Pi1, Pi3, Pi5, Pi6, Pi7. With this left edge of this one. So in the tree, and the other one was Pi1, Pi3, Pi5, okay, Pi6 and Pi8. That is another terminal case. We are not considering P7. That is actually the right edge of Pi7. So everywhere you try to explore, you will find out the cost is this one. Okay. So this is another solution you can see. So in both the solution the cost is 5, which is higher than the initial explored value. So we retract. So we may select an alternative path by saying Pi6 equal to 0. We can easily see that again the cost will be equal to 5. So here the solution will be Pi1, Pi3, Pi5, Pi7 and Pi8. So this is this solution. This is this solution. Sorry. this is pi 7 and pi 8. Everywhere it will be 5. Now you explore the whole tree, you will find out that everywhere the solution space will be 5. That means what? In this case, this is an example. This example illustrates how the branch and bound algorithm works with this heuristic, and also it gives another example. And another fact is that we have landed into a problem, because here in case every part of the tree almost you have to explore, because your heuristic was giving you a wrong value of 1 in many of the cases, or it was wrong value of a lower, or it was giving a very tight value of lower bound. Lower bound computation was very tight in this case, towards very much negativity it was there, and so you have to explore the whole tree, and everywhere you were getting the value the 5-hour tree. So in fact you have to explore most of the tree. Okay, so then you can say that why is it like that? How is that lower bound computation improving my solution? It is not at all improving my solution. At least in the, if you don't use the heuristic also you have to explore a large part of the tree. Here also you have to explore the lot of the tree, because nowhere it is, here is actually everywhere it is giving a hope that the cost is 1. So you add it, 3 plus 1 is 4, you go and you may get a solution. Here also if you try the other parts, you can also see it will always tell you that you can have a solution which is equal to 4 every time you go on exploring it, and you will find the cost is 5 and you are in a problem. So how does it help you? So I mean then why actually you, I mean then what is this what is the advantage of this heuristic? Okay, now in the question answer solution we will see that we will just slightly modify this lower bound computation heuristic, and you will see that really the fruit of this lower bound computation is coming into picture. Okay, so let us just see. So what is the question? The question is saying that the lower bound estimate algorithm discussed in the lecture may not always give a sharp bound. We suggest suitable modifications and show how better bounds can be obtained. Also show using the example how benefit is achieved in branch and bound with the modification. Because in the exam, because in the lecture flow we have seen that with the, as the bound was a bit strict, that is your bound was actually giving 1, and then it was 3 plus 1 4. You were prone to explore in the past, but finally you are finding that the cost is 5, and then you are actually higher than the initial cost, and you have to explore the full space. And then you will find out that nobody can give a solution in less than 5. So you have, the answer is 5 mean terms, 5 prime implicants, and you take any one of them. So unnecessarily you have to explore the whole tree. So we will just see a very good, I mean what you can say, if I tell you we will give you a very good, we will try to improve upon, I should not call it a very good improvement on the heuristic, but we will give you some improvement on the heuristic, because more improvement you make on the heuristic, slowly the heuristic will become more and more complex and will take more complexity in time. So that way our idea is not there. So you have to make the heuristic as better as possible, subject to the complexity, that is you should not take a very huge amount of time, and yet what your gain should be visible by not having to explore the whole part of the tree. So let us see what small modification we have done. So add a w which is equal to the number of ones in the row. Same thing you do, choose the minimum row. If there are multiple row, choose the one from the top. Same thing we are adding weights and ascending in ascending order. Delete all rows where there is a common ones in the rows. So if you delete all the rows where there is a common ones in terms of some columns, then also delete Ri. Now what you have to do, we have at this bold line says that we have added a very small computation. If after deletion no more rows remain, then check if there exists a pi such that a pi has all ones. If there is no such column, then 1 needs to be added to the lower bound. Okay. So now what happens, it sees that you go for a terminal case. Now in the case where you are actually what we are doing, we take one row and find out where there are common ones. Okay. So if they are finding out the common ones, you reduce, you eliminate those rows. Now if you, it says, the bold line says that if you reach a case when all the rows are eliminated, then you say that the bound is now added 1. Say for example you take one row and say all other rows get eliminated, then you say that now it is adding 1 to this one. Now we are adding one more weight to the lower bound. So adding one more row, adding 1 to the lower bound and all the rows getting exhausted means if you cover the corresponding column, all the row gets covered. So here we have put a small thing, just if you want to add a weight 1 and everything gets finished, just to check that whether there is a column where everything is a 1. If everything is not a 1, there is no meaning of putting a lower bound equal to 1, you just add a value of 1. That is very obvious, because if you say that by taking only one column everything gets eliminated, that means there is a column where there are all ones. If this is not the case, it will be a bit higher. So in this case we do not find out what is the value which is higher, we just add 1 to it. Like for example, if you just see this, so in this case what happened, you say that you take this one, it gets eliminated by this commonality, and this one gets eliminated because of this commonality, and you said the bound is 1. So in this case we put one more check saying that is there any column where everything is a 1. If this is not the case, you add a value of 1 and say that the lower bound is 2. Now why is it? Because if you say the lower bound is 1 in this case, that means there exactly exists a column. If you take that column, then all the 3 rows get eliminated. But if there is no column with all ones, then this is actually a false value. So you have to add a 1 to this. This is a slight modification we have done. But it may, why we have added 1? Because we want to keep the thing simple and just repeat the whole thing. Okay. So, this is this case. So, just I told you that if you take this, so you will say that this one is common with this one, eliminate this one is common with this, eliminate this. Now, the value is actually 1, but again there is no column with all 1, so you have to add a 1 with this one. So, this what is the heuristic, whatever for the motivation of this one is written in this paragraph, you can just read through it. Now, again we take the whole example, now not going to it, and will slowly show you the benefits. So, this is our old example in this case. So, the lower bound in this case is 4 if you go by the old technique. Okay, so, now if you go by, if you find out the 1357, if you are using this old lecture, if you just find out the values and all, if you find out in this case the value is 2, in this case the value is 2, in this case the value is 2, and then if you try to reduce this, you will find that the answer is 1, 3, 5 and 7, that is going to be your answer. Okay, and you get the 4 if you are using the old heuristics, you will get the value. Now, what we have done? So, in this case, now this one last element will be your this guy. Okay, so now you are having 1, 3, 5 and this one you are having. So, now in this case, you will find out that if you take Pi 7, okay, this one will exhaust all the rows, but need to 1, but in this case if you take now eliminating mean term 7. So, in this you will be, if you keep on reducing this, you will find out that we will reach a situation over here. In this case, after eliminating mean 7, we exhaust all rows, but need a 1 to the cost, because there are no 2 rows Pi 7 and Pi 8 which are having all 1s. So, let us see what does mean by that. So, in this case, if you start eliminating all the rows and all which I have seen, so in this case what you will land after the third iteration, first iterations you will end up in taking 1, 3 and 5, and then we will have the following matrix. After we eliminate mean term 7, we will exhaust all the rows. Okay, we will exhaust all the rows, we will find out that we have exhausted the whole stuff, and so obviously some 7 will be added. Okay, now you will say that the lower bound is equal to 4, 1, 2, 3 and for plus 1, 3, and for this 7 you can take 7 mean term 7. So, so you have to include mean term 7 also. So, it will be 1, 2, 3 plus 1, 4 will be there. Now, so actually the answer is that is the inclusion of the mean term 7 is actually adding a value of 1. But if you look at our heuristic, it will add the value 1 more. Now, why is that? We are saying because after eliminating mean term 7, we will exhaust all the rows, but we need not add 1 to the cost in this case. Why? We will see, because there are 2 rows Pi 7 and Pi 8 which are all 1s. Okay, so now what is the case? So, I am just telling that what we are doing, we are actually exploring this lower bound value for the initial matrix by our method, not by the old method. By the old method, if you apply, you will get 1, 3, 5, 7 and your cost will be equal to 4. But in our case, in the terminal case, what you are going to find out, in this you will be in the last case, this matrix will be available to you, and in this case you will find out that 1, 3, 5 already has been taken. So, we will be adding 7 because it will now finish up the row. Now, whether for 7 you will be adding a value of 1 or whether you will be adding a value of 2. By the old heuristic you will add the value of 1. By our heuristic, what we will add? Our heuristic also in this case you will add a value of 1, because there is 2 columns where the value is all 1. In this case this is very simple, because there is only one, actually the row is 1. So, obviously you can say that this column has all 1s and this column has all 1s. So, by both the techniques, by our heuristic, modified heuristic and the previous heuristic, the lower bound will be equal to 4. But now see what will the advantage will be. So, here actually in the broad full matrix, the lower bound by the old heuristic and our modified heuristic is the same, and that is equal to 4. But we are not added, but only thing you have to note that in the old example, they will include old heuristic, they will take mean term 4 and they will say that the value is equal to 4. But our case, we will see that, we will also say that the value is 4. We have added 7, we have added the value of 1, but we are not adding the value of 2, because we have 2 columns where there are all 1. So, for the big matrix, both of our heuristics are given the same algorithm. Now, again we are doing all these things. So, if you remember, so if you are taking you are taking mean term 1, 4 and 12 are covered. So, you take Pi 1 old case. So, mean term 1, 4 and 12 will be covered, this will be dominated, Pi 3 will become essential. So, the reduced matrix after taking Pi 1 and Pi 3 and eliminating this, we get the cost of the following matrix. The cost of the solution is this one. All techniques, all thing we have done, and if you remember, this one are reduced matrix. Okay. Now, if you see in this case again, the lower bound is 5 and 7. If you take the old case, the lower bound is 2, 5 and 7 is same as the original lower bound computation as well as the modified one. So, we explore on this matter as a solution place 2 plus 2. As on this value is equal to the lower bound, we explore this. Same thing we are doing with the 5 is being taken. So, you take 5 old case and start exploring the matrix. So, if you take 5, obviously Same thing if you do. So, if you remember, if you take pi 5 is being taken, what happens? Row number 9, 10 and 11 gets eliminated. So, if you take this the common, so this will get eliminated, and then again some row dominance column, these two will be getting dominated and explored, and finally if you remember we are going to get this matrix. Okay, now here again we are, if we try to see, that is the old, I mean the same flow, this one, if you start with this one, this is the same flow we will get over this by the previous example we discussed, and finally we will get in this solution. Now here we are going to find out that there will be a difference in the heuristic, our heuristic and the old heuristic, and the old one we discussed, the modified heuristic and the old heuristic, we will find a slight difference. So in this case, if you find out that what is the lower bound, again I will ask, even the old heuristic will tell that this is common, these two are common, so the lower bound is 1. But now again you have to find out that by modified heuristic will check that before reporting a lower bound of 1, is there any column where there are all 1s. In this case it will find out there is no such, so you will add the value of 1 and the lower bound will be now 2 by our modified. This is our modified, and by 1 it will be by the old one. So now we will get, you are reporting a lower bound of 2, and the old example, old heuristic will report a lower bound of 1. So now it will say that now what is the cost? The cost is pi 1, pi 3, pi 5 plus 2, that is equal to 5 by the new heuristic. By the old heuristic it will be pi 1 plus pi 3 plus 1 is equal to 4. So you will be prone to explore some of the paths. By the modified heuristic it will be 3 plus 2, it will be 5. So at that time what it will say that it is higher than the initial estimate of 4. So you do not explore on the path, okay, and then actually you are going to get a, so in this case the lower bound was 1 comprising 6, but using the modified one the lower bound will be equal to 2. So our case it will be 5, okay, then it will say that do not explore on that path because the bound is higher, and then you will be saved from actually taking some of the paths. I mean just let me tell you what happened. Just what happened. So in this case, I mean this is the same old tree, but what will happen in this case is actually we will be going through this path. So here actually our, I mean here it was 1 plus 2 plus 3 plus 4. So it was 3 plus, our case was reporting, old heuristic was reporting a value of 1. So it was saying that it is 4, you keep on exploring in this path and finally you are getting 5 and you are having a big problem. But in the modified heuristic here we will give a lower bound of 2. So 3 plus 2 will be equal to 5. So it will say that do not explore on this path, do not explore on this path because the value is equal to 5. So immediately you will backtrack here and you will find out that you have reduced, you have gone by exploring less number of paths, and finally you will find out because the obviously lower bound is 5, nobody can give you a solution less than that, because the lower bound 4 which was initiated by the our heuristic or even the old heuristic, the initial value was 4, that was a wrong estimate, minimum value has to be 5, but by using the our heuristic or lower bound computation heuristic, everywhere you will find that the cost is 5, 5, 5. So you will not explore this part of the tree, and finally in the last leaf node where this will be, you will find that there is no more solution is left. So you will come to the solution that obviously 5 is the solution. So in a nutshell what we have achieved. So you can find out that before I close, just we see what happened. So initially we started with the Bayes matrix and we have taken a old heuristic and a modified heuristic. Both of them has given a lower bound of equal to 4. And in fact we found out that that is not the correct bound because minimum 5 has to be taken. But then what is the gain? So the gain was, so you started exploring in the process which is already explained in details a few slides back, and finally we landed up into this matrix. So if you take the old heuristic it will say the lower bound is 1, but if you take our heuristic, that is modified heuristic, so it will take that, it will say that the lower bound is equal to 2. Then it will say that the lower bound is 5. So you will not explore many of the paths of the tree until and unless you go to a path which is the last case to be, because there is no more path to retract, then you will find out this is the only path that has to be explored because all other paths has been exhausted and you have not explored those paths really. Every path you check, okay, the cost is 3 plus 2 5, 3 plus 2 5. So everywhere you will stop, and in terminal case you will find that there is no more case to explore. So you have to by default go in that path and you will find out the cost is 5, and you will say that the initial lower bound estimate 4 was wrong and the cost is 5, and this is the solution. So what we have saved the exploring all the paths and just going to the terminal case directly. But if you take the old heuristic where this one is reporting a lower bound of 1, so you will keep on exploring all the paths, and at the end of all the paths you will realize the value is 5, again retract the value of 5 and keep on going through it, and you exhaust all the case, then you find out that I have reached a value of 5 and that is the solution. But unnecessarily you have explored so many paths, that was not required. So by the modified heuristic we have achieved this one. Okay. So with this, actually this is what is being told. So with this we come to the end of this lecture and this module, And what we have seen that we have taken the unit covering problem, then we have found out an algorithm or in case a bunch and bound algorithm which can give you the subset of prime implicants which can cover or cover the function. That is what we have done. But again you can see finding out all prime implicants by tabular method or by iterative consensus method, then again you have to make a table and make a matrix and all. At some points of time you have to explore the mean terms. Exploring the mean terms means it is strictly an exponential case in the number of inputs. And again if your algorithm is again taking some complexity on that, so it is on the order of 2 to the power 2 to the power n, if n is the number of inputs. So if n is the number of inputs, the constant matrix may be of the order of 2 to the power n, correct? And then some again exploring some other solution on that will be again order of something of 2 to the power n. So it was a fairly complex algorithm, and we tried to make it somewhat minimal or somewhat reduced by using the heuristic and all. In the next lecture, that is that is the next module, what we will see is that we will not at all go in terms of mean terms. Representing a function in terms of mean terms or a matrix in mean terms itself is an exponential problem. So we will not go to that. Directly we will put on some heuristics and try to get a solution. That is what we will be looking in the next lecture. Thank you.